Hello and welcome to EDGEcast, the series where we show you tips, tricks, and best practices when using Solid Edge. Today we'll be looking at the variable table, and how you can use it to create automatic model updates. If you're unfamiliar with variables, or if you've got a basic knowledge of how they operate, but want to know more, this video should be useful to you. Before we begin, just bear in mind that I'll be working mostly with synchronous mode, but in ordered mode the basic principles behind variables are exactly the same. I'll start off by explaining what variables are, and where you can view and edit them with the variable table. Then I'll show you how to create rules and formulae to drive variable values, how to link them together, and expose them for use in draft environments. Finally, I'll show you how to use .bas files to make your own rules, if the ones already present in the software don't meet your needs. So, if you've never opened the variable table in Solid Edge, you may be asking, what are variables? A dictionary would tell you that these are elements that will change, but in Solid Edge specifically, variables are numerical values that can be stored inside a Solid Edge file and then be used to drive model parameters. Whenever you add a model dimension, enter a pattern count, or set physical properties, you're creating variables in a table that can be opened from the Tools tab in Part, Sheet Metal, Assembly, and Draft files. Variable tables allow users to add rules and formulae to them, to limit the input values model features will accept, or control what the variables are, depending on certain conditions. With copied links to other variables, it's also possible to make one variable dependent on another. For example, if you always wanted a part's width to be equal to twice its length. This is the variable table as it appears in Solid Edge 2019. Now there was a major update to variable table functions at ST9, so if anyone watching this is familiar with variables at ST8 or before, you might be surprised at exactly what it can do now. It's found under the Tools tab, and if you're thinking, that looks quite a lot like an Excel spreadsheet, well then I'll say, yes, that's the idea. There are quite a few similarities. It doesn't work exactly like MS Excel, but many of the simple maths operators are exactly the same. At the top of the variable table, you have commands such as the ability to assign unit types to a selected variable, then the two list options. Of these two, List displays a flat list of variables, and Structured View sorts them into folders based on type, whether they are physical properties or user-defined, which ordered feature they affect, etc. Sorting can be carried out on the different columns, and the Filter button allows only certain properties to be viewed. Finally, we have the Formula Wizard, which can be used to generate complex mathematical rules for your variable values, and the Rule Editor, which I'll demonstrate in a little bit. The columns in this table can't be deleted, although they can be shown, hidden, and reordered if you right-click the top of one column and choose Columns. There are two types of variables stored in this variable table, dimensions and variables. Dimensions, as the name might suggest, are dimensional relationships in your model, such as distance or angles, and variables are either physical properties in the model or ones that you created yourself. Name has to be unique for each variable, and it can be changed. By default, a dimension will automatically generate itself in the table, with the first letter being V, followed by a number. So if you ever see a variable in this table that begins with the letter V, chances are it's a dimension somewhere in the model. All variable names have to begin with a letter, and there are restrictions on the name you can use. For example, spaces aren't allowed, nor are any punctuation marks. Beyond that, though, any name is permitted. Documentation does mention a 40-character limit, and although I found this didn't actually stop me from entering a very long variable name, I'd still advise that less is more when naming variables. You want something short and easy to read. Variable values can be edited if their cell appears white. If it's grey, then it means it's governed by a formula or a logical expression. Also, you can only enter numbers in this column, and the number of decimal places for each variable is fixed for the different unit types we find. For example, a temperature variable would have 4 decimal places. Another column that you might be interested in is the rules column, which can be used to restrict variable values. The most common rules are as follows. Blank, which means no rules are controlling this variable. Paste link means that this variable is driven by an external file. Formula means that there is a mathematical formula driving this value. Discrete means that the variable will only accept certain values. And finally, limit allows users to set a variable between certain minimum and maximum values. All of these allow you to create design intent in your models. If you know, for example, that your part can't exceed a certain size, it's easy to do so here. The final 4 columns are formula, which shows what the function is that controls this variable, range, which shows if there is a range limit, expose, which tells us if the variable can be accessed as a custom property in a draft file, and finally a space for user comments, which might be useful if you've written a rule to address a particular product requirement. All of what I've said until this point is theory, so let's put it into practice. Here's a simple example of a bearing block. I've made it in synchronous mode, but I'll be showing an ordered model at the very end. As I said, the principles are the same. Let's see what dimensions are attached to this model. Let me turn on PMI. There, we've got some locked dimensions in place, which display in red. That's important to remember, as a dimension can only be controlled in the variable table if it's locked. Speaking of which, let's go to the variable table. It's found under the Tools tab in the section called Variables. And here it is. I'll just drag this off to the side of the screen. You could drag it to another monitor if you've got one. My part's obscured, so let's pan the view across. Variable table doesn't stop you from moving the model view around. You might have noticed this is quite a long list, and that's because I assigned a material earlier, so all the physical properties have been filled in. I can expand the table, but that's still a lot of properties. I'm currently in list view, which shows a flat list of all the variables I've got, and before ST9, this was the only view we had. Now, though, we can see this list in structured view. Structured view puts all of the variables into collapsible folders, which can make the table a little easier to view. We have separate folders for procedural features, like holes and patterns, and PMI dimensions in another folder. PMI dimensions are interesting, because when you highlight one in the table, the dimension highlights itself in the 3D view. Physical properties are minimized by default in structured view because, well, as you can see, there's quite a few of them. In list view, it's also possible to filter out certain variables by type if they're not useful at the moment. Let's bring up the filter menu and click to deselect physical properties. That's much clearer, and very useful if you don't particularly care about read-only variables, like mass, volume, radius of gyration. Now so far, we've seen variables that Solid Edge added for me as I modelled, but I can add my own. Double-click on an empty name box and enter a value, remembering the rules about variable names. It has to begin with a letter, no special characters, and be less than 40 characters. Underscores are allowed though, so custom underscore variable is just fine. Now the value has to be a number. Let's choose a unit type as well. Distance will do. Now that's added to the variable table, but it's not doing anything right now. I want to use it to drive one of these PMI dimensions. Let's say this one. If I float my mouse over it, we can see it's called linear 9. Of course, I could always click on dimensions to check which one it is. Let's rename it, shall we? This is the part depth. So now to link it to my custom variable. The formula box will allow you to type an expression directly into it, a little bit like an Excel spreadsheet. This part depth is going to be exactly equal to twice the custom variable, which I can add into the formula by left-clicking on Custom Variable's name. Now let's hit Enter. That does 3 things. It sets part depth's value to 60, it grays it out, and turns the PMI dimension purple in the view window. Purple meaning that the value is driven by a formula. Now for something that people often miss, deleting custom variables. Let's say this one isn't very useful, and I want to delete it. If you click on any of the cells in this row and hit delete, it'll try to clear the cell value only. To delete a variable, you need to click just to the left of the variable type column to select it, then hit delete. You can only do this for variables you added manually. Back to the part depth. If this needs to change, we now can't enter a value in this box, because it's grayed out. Instead, we need to edit something driving it. In this case, custom variable. Because this cell is white, we can enter any value we want. And yes, in case you're wondering, we can do this to PMI dimensions in the table. If you decide that this formula isn't relevant anymore, Click on the formula cell and hit delete. If you still want to create formulae, but you don't want to have the variable table taking up screen space, you can create formulae directly by editing a dimension. Single-clicking a dimension's number will let you change its value, but double-clicking it will let you edit the formula driving it. Alternatively, right-click the dimension and choose Edit Formula. It's possible to link to other dimensions while in this mode by left-clicking them to write them into the formula section. And you can also display dimensions formulae instead of their values by right-clicking one dimension and clicking Show All Formulas. Just bear in mind that's a setting for the whole of Solid Edge, not just one dimension, so be prepared to change it back with the Show All Values. If instead you want your variable to be driven by a specific maths expression, or maybe a limit, you can use the Variable Rule Editor. You can reach the Rule Editor in one of three ways. In the variable table, click on Rule Editor here, or you can right-click on the variable name and select Variable Rule Editor. Or the third method, without the variable table, double-click on the PMI dimension value to edit the variable, open the drop-down menu next to the green Accept button, and click on Variable Rule Editor. What this does is opens this window right here, where you can drive the variable value. This can be done with a formula, same as entering a formula directly into the table, or with a pasted link from another variable, or with a limit. Variable limits come in two subtypes, a discrete list, or between minimum and maximum limits. As you can see here, these limits can be either a value entered by the user, or they can be driven by yet another model variable. At this point it's worth mentioning that you can create incredibly complex model update behavior with enough time in this table. Just make sure that all the rules you had make sense in a real-life engineering scenario, or you might get unrealistic model changes. Beyond that, let your imagination run wild. If there's a particular rule-based restriction on your model, the chances are there's a way to set it up. Without any further ado then, let's see the rule editor in action. Back to the variable table we go, and let's set up this screen again. If you don't have one already, multiple screen setups are incredibly useful for this kind of work. Let's change some variable names for a start, such as part length and part width, just to make them more logical. That's just for ease of use though, you could keep all the variable names as default if you like. Now that that's done, we'll select part length and dive into the formula editor using the first method I mentioned. Just push this button. I know that this part has a particular requirement. Its overall length must be no longer than 250mm and no shorter than 100mm. So I'll use the greater than or equal to option and set a value of 100mm for the minimum. If that was all, I could hit OK, but remember, it needs to be shorter than 250mm. So let's use less than or equal to and enter 250 for the maximum. Then when I hit OK, it adds this information to the range cell, and a rule type is defined. Another requirement I have is that the part width must only be certain values between 100 and 130mm in increments of 10mm. That means a discrete list. To create a list of values, enter a number here, add a semicolon, add another number, and repeat until you have all the values you want. This changes the range cell, just like the limit we added earlier. That's all well and good, but how are these rules enforced? Let's say all this took place at 5 PM in the design office. The part was saved, and I went home. Now a completely different user opens the part. Let's call him Steve, and he wants to change this part's length to 300mm. You might try to do so with synchronous moves, but, of course, a locked dimension prevents that. No worries, Steve knows how to edit dimensions, so he'll go ahead and click on the value, enter 300mm. But no, this information box comes up, and those are the details for my rule. It tells Steve which values are allowed. And now with that information, he can change this to 250mm, as that is allowed. Now Steve wants to change the part width, and he sees that the dimension's locked, so once again, he'll click on it. Instead of a white value box, though, he finds a drop-down menu of possible part widths. That's what a discrete list will create. It's much more restrictive than a simple max-min limit. Let's go down to 110mm. Just bear in mind that in synchronous mode, dimensions and variables are only one of 3 ways you can limit geometry changes. My design intent live rules need disabling for this move to work. For more information, I'll link my synchronous modeling EDGEcast episode below. We also run an in-depth synchronous training course, if you're interested. As you can see, Rule Editor is great when you have set-in-stone requirements for model dimensions, as it stops other users from accidentally breaking these rules. So far, though, I've been treating this part as if it's modelled just on its own. In reality, parts are often modelled as part of an assembly, meaning that model dimensions might need to be driven by another source. That's possible in 2 ways. You can open a second Solid Edge file, and then copy a link to one of its variables with a right-click, Copy Link. This can then be pasted into a formula cell in your first file with right-click, Paste Link. Alternatively, if you have an Excel spreadsheet, you can copy a link to one of its cells with the same method. What this means is that you could create an external part configurator document to drive key dimensions in your model. The only risk with using variable links is that should your linked files be moved around without Design Manager, this variable rule won't update unless the formula is updated first. We often see this sort of problem on support, and while there are ways to fix broken file links, we recommend keeping linked files in place wherever possible. Let's show how both of these pasted link methods work. If I had a bolt which was meant to fit exactly into this cutout, and I don't want to use part copies, I could copy a link. Notice how I didn't need to close my variable table. It updates to show variables from the currently active part. Here's my bolt's shaft length. So let's right-click the variable name and copy a link. Back in the bearing block, I have a variable that controls the hole depth, linear 6. To link it to the bolt shaft length, I'll right-click the formula cell and paste link. Because there's design intent live rules active, I get another message saying that other relationships were found, in this case to base reference planes. That's fine, so I'll rename the variable to hole depth. Now there's one more variable I want to link, the height of the hole in this bearing block. There's already a dimension in place. All we need is a link. Now earlier on, I saved an Excel document with several cells filled in with values, so let's Alt-Tab over to it. Here it is, a nice simple table. No Excel magic going on in the background, although you could have extra logic here if you want. All I want, though, is to copy one of the cells. You could do this with Ctrl-C if you wanted. Back over to Solid Edge, and let's change this variable name to hole height, and link it to the Excel document by selecting Formula Box, right-clicking, then using Paste Link. If I then go back to the Excel document and change the hole height value to 60, the part automatically updates. The hole is concentric to the outer wall of the bearing block, so that's moved as well. One more thing though, when linking Solid Edge files to Excel documents, it's best practice to open the Excel file first, then Solid Edge, to make sure that links update cleanly. One variable table column I haven't talked about yet is the Expose column, which contains a series of checkboxes. Checking these boxes means that the variables are stored as custom file properties, and you can see this yourself by ticking the boxes and checking file properties. You might be asking, why is this useful? And the answer is that anything stored as a custom file property in a Solid Edge model can be added as a draft callout. For example, you might want to add a draft callout of the X and Y count of holes in a rectangular pattern. The way to do this is to expose X and Y count in the part file, then add a particular callout. It's easier to show this process than to explain it. Back to the bearing block we go. The observant among you will have noticed that these holes here are arranged with a pattern called Pattern 1. Because it's a rectangular pattern, we have X and Y counts stored in the variable table, along with a pattern area. Both of these need to be seen by the technician making this part, so let's expose both of them. Exposed name is an optional column that allows you to write an alias for this variable that only the draft environment will see. Let's call this one hole pattern 1 X count, and the same for Y count. Now the part's ready to be drafted for manufacturing. Always save your work, remember, and I'll go ahead and create a brand new drawing. I'll place 3 views, that should be enough for now. And what I want to do is add a callout to show the whole pattern count in X and Y. And that means the callout command. Now for property text. Remember, whole count is a property now. They're stored in the graphic connection to part property list as both exposed variables and custom properties. I'll add Y count first, then use the same process to add X count. I'll also add some free text in this callout to explain to the production technicians what the resulting numbers mean. Once that's done, I'll attach the callout to the parts drawing view. And there we have it. Just to prove that's worked, let's edit the bearing block's pattern count. Let's try setting this up as a 3x2 pattern. Well, that's not right, I've got my X and Y mixed up. I'll tab my way back to the X count. That's going to be 2. The Y count, which has to be 3. Much better. My drawing says it's out of date, as you might expect, so let's update the views. And there we go. Not only does the view show the new holes, but the exposed variable callouts have updated to show the correct Y count as 3. I'm almost finished with this EDGEcast episode, but I want to show you one last thing. The function wizard, which can be used to drive variables with logical arguments and maths functions such as trigonometry, logarithms, exponentials, etc. This was heavily enhanced at ST9, and I advise taking a look through all the functions that are available now. For example, if you want a certain variable to be equal to the sign of another one, then choose the sin function from the list, and then choose Next to select the inputs for it. In the event that you want a particular rule to be defined, but none of these functions here are suitable, you can always write your own, as Function Wizard also accepts .bas files containing logical expressions. What this means is that your potential variable rules are limited only by your skill with Visual Basic. For example, before the introduction of the if function in Formula Wizard, users had to create a script like this one here to create an if statement. There's a Microsoft Visual Basic script guide linked below, so take a look if you're interested in learning how to write your own scripts. These days we can create if functions without an external script, but if only allows 2 possible cases and outcomes. So, what if we want more than 2 possible outcomes? Here's a pipe elbow I made earlier in ordered mode. I did this just to show the difference it makes to the variable table. I know from my flow calculations that if my pipe diameter is more than 100 mm, then I'll need 6 bolts. And if the diameter is 150 mm or greater, I'll need 8 bolts. Clearly this needs a variable rule to be added, but how can I get this to update automatically with just one rule? Let's go into the variable table. And here's the main difference between synchronous and ordered variables. In ordered mode, and with structured table view, variables are sorted into folders by the feature they affect. This sketch contains a variable governing the pipe diameter, and pattern 1 contains the number of holes. I've renamed both. There's additional logic governing flange size and hole pattern diameter, but I won't go into that. Instead, I want a formula to control the number of holes in the pattern. To do that, I'll go into Formula Wizard. I'll say that I've looked at each of these and decided I don't want any of them. If, as you can see, only provides a single condition and true value and false value, with a potential for 2 outcomes. That won't do. I have 3 possible outcomes. Fortunately, I already wrote a script for this. Now here's a restriction you need to bear in mind. The file path to a script file and the file name itself must not contain spaces, so be careful where you store your scripts. I know that the script contains a function called diameter holes, which contains if, else if, and else outcomes from one input. Be careful with this function selection, as the first of these is the function I need, and the other one here is the script file name. Once I've selected this, I'll enter the variable names for pipe diameter and hole number. I have 2 possible methods of entering variable names. I can either type the name manually, like this, or I can right-click and copy it from the name cell, like this. And then I'll hit Finish. Nothing's changed yet in the model, but now the hole pattern count is linked to the pipe diameter value. Up to 100 mm diameter, there's no change in hole number. But if I increase it to 150, the pattern count jumps to 8. And now back to 4. and if I put in a value between 100 and 150, the pattern count goes to 6. What we have now is a part with enough intelligence to update its own hole count when its pipe diameter exceeds a certain size. Just for reference, here's the code I was using to drive that model. All I did was write this up in Notepad and change the file extension from .txt to .bas. I didn't even need to use Visual Basic. If you're feeling confident, you could use select case statements, maybe obtain inputs from other files, but my code's much simpler than that. I am not a Visual Basic expert, so bear that in mind before you copy this code to use in your own work. If you want to write something really complicated, I'd advise doing some VB training first. In summary then, I've introduced the concept of variables in Solid Edge and how they can be controlled by user-defined rules of many sorts. I also introduced the concept of variable linking, even between different variable tables, or from an Excel spreadsheet. And finally, we looked at using Visual Basic scripts to govern variables with even more complicated logic. Thanks very much for watching, and if you have any more questions, topics you'd like to see covered in future videos, or other feedback, please either leave a comment below or send them to us by email at support@cuttingedge.co.uk. And be sure to tune in to watch the next episode of EDGEcast, where we'll be looking at how to store and reuse part and sheet metal features with feature libraries.